Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. All right, imagine this. You're in a lab late at night. Three leaderboards are open on your screen. Same models, same task, completely different rankings. One benchmark says model A is the best, another swears model B is superior, and a third one shrugs and says they're basically the same. At that moment, a quiet but uncomfortable question appears. What if the benchmark is wrong? That question is exactly where the paper Benchmark² Systematic Evaluation of LLM Benchmarks begins by Qian and Chengsong Huang along with collaborators from Fudan University and industry. And instead of asking which model is better, this paper asks something far more dangerous. How do we know if a benchmark itself is good? Because here's the story we usually tell ourselves. We train bigger models, we run them on famous benchmarks, we trust the numbers, and we move on. But the authors show that this trust is often misplaced. They identify three recurring villains hiding inside modern LLM benchmarks. First, ranking inconsistency. Two benchmarks, same domain, same models, totally different rankings. If benchmarks disagree, which one is telling the truth? Second, low discriminative power. Sometimes a tiny model and a massive state of the art model score almost the same, not because they're equally smart, but because the benchmark is too blunt to tell them apart. And third, the strangest one, individual questions where a weaker model succeeds and a stronger model fails. That's not just noise, that's a signal something is broken. So the paper introduces a framework called Benchmark², not a new benchmark, but a way to evaluate benchmarks themselves. Think of it like a quality inspector for evaluation. It uses three core ideas. The first is cross benchmark ranking consistency. If a benchmark is measuring the right thing, its model ranking should broadly agree with other benchmarks in the same domain. If it constantly disagrees, that's a red flag. The second is discriminability score. This checks whether score gaps between models actually mean something. Wide, meaningful gaps are good. Tiny cluster scores, that benchmark isn't pulling its weight. The third and most interesting is capability alignment deviation. Instead of comparing totally different model families, the authors stay within a family, same architecture, different sizes. And they ask a simple question. How often does a smaller model outperform a larger one on the same question? Each time that happens, it's counted as an inversion. Too many inversions, and the benchmark is probably testing quirks instead of real capability. Here's the clever part. They don't just analyze one benchmark. They evaluate 15 popular benchmarks across math, reasoning, and knowledge tasks. They test 11 models spanning 4 different model families, and the results are uncomfortable. Some famous benchmarks turn out to be highly consistent but barely discriminative. Others separate models well but violate capability hierarchies. A few perform poorly on almost every metric. No benchmark is perfect. But then the paper does something surprisingly practical. Instead of throwing benchmarks away, they selectively trim them by keeping only high quality questions, those that are discriminative and capability aligned. They reduce benchmarks to about 35% of their original size, and yet the model rankings barely change. Same ordering, better stability, higher signal, less compute. That's the punchline. The problem with LLM evaluation isn't just model scaling, it's measurement quality. A practical tip if you're evaluating models today, don't trust a single benchmark score. Check whether that benchmark can actually separate models and whether stronger models behave like stronger models. And a key pitfall to avoid, optimizing for leaderboard position without questioning leaderboard quality. That's how we end up chasing noise. The story this paper tells is simple but powerful. If benchmarks guide progress, then broken benchmarks quietly mislead an entire field. And Benchmark² doesn't claim to fix evaluation forever, but it gives us something we desperately need, a mirror. So the next time a new model tops a leaderboard, the real question might not be, is this model better? But is this benchmark worth believing? If you found this helpful, hit like, subscribe, and comment which AI system you want to build next. Stay sparked. See you in the next video.